When a star several times larger than our Sun is on its last legs, it goes out by generating the most spectacular blast ever observed by the human eye, a catastrophic hypernova. This phenomenon is so bright that it can outshine an entire galaxy of hundreds of billions of stars, and is so powerful that it can generate more energy in a single day than our Sun will generate in its entire lifetime. In fact, a hypernova is the most powerful explosion in the galaxy, coming second only to the Big Bang. Roll up your sleeves and put on your smart glasses, because we're going to crack together the science behind hypernovae. In order to do that, we first need to dissect its smaller brother, the supernova. There are two ways this kind of smaller explosion can be formed. The first one can occur in systems where two stars orbit one another in a binary system, and the other comes from a white dwarf. When a smaller-sized star runs out of the fuel in their core and are about to die, they eventually turn into white dwarfs. With no source of internal energy, their gravitational collapse causes them to become extremely dense, sometimes reaching densities 200,000 times that of the planet Earth or more. As a reference point, a typical white dwarf is half as massive as our Sun, yet only slightly bigger than Earth. Their fate is to slowly cool down until they're completely cold, at which point they become black dwarfs. In a binary solar system where two stars are so close together that they orbit each other, one carbon-oxygen white dwarf can start pulling matter from its brother star, and it becomes more dense as mass piles up. When it exceeds a critical point of density, the star inevitably detonates in a fantastic bang, forming a supernova. The second type of supernova is formed during the death of giant stars. When a star at least 5 times the size of our Sun is about to die, it'll go out in a massive cosmic explosion. During their whole lives, all stars survive because of the delicate equilibrium of two powerful forces: the star's own gravity, which fights to compress it into an extremely tight ball of mass, and its opposite, the star's outward pressure generated from the nuclear fuel burning in its core. When a star burns all its nuclear fuel, gravity starts winning, and this million-year-long battle eventually ends up with a catastrophic collapse. Enormous shock waves are generated at such a quick pace that the outer part of the star explodes, generating a bright and powerful explosion. A typical supernova may shine with the brightness of 10 billion suns and generate 10 to the 44 joules of energy. Astronomers estimate that, on average, about 1 or 2 supernovae explode each century in our galaxy. The last time Earth felt the effects of a supernova was about 1.7 to 3.2 million years ago, but thankfully, the explosion took place 325 light-years away, which is 6.5 times farther than the danger zone of 50 light-years. Earth, however, was still affected to some degree. What is the case with hypernovae, though? Even though there are a few differences in the science behind them, a very simplistic definition would be that a hypernova is a supernova on steroids, generating an explosion which is 100 times more powerful. Hypernovae are so powerful that the energy they release in the first few seconds of the explosion can be 10 to the 16 to 10 to the 19 orders of magnitude greater than that of the Sun. This means that a single hypernova can supply our Earth's energy needs for 1 billion years, if not more. Astronomers think that they have a good handle on what causes an average supernova, but this is not the case for hypernovae. You see, the latter are extremely rare, and we only have estimated a few dozen of them over the past few decades. The experts are still not sure what causes a hypernova to be so colossally more impactful. We're going to show you the 3 leading scenarios for hypernovae formation. In the first case, the collapsed star or collapsar model states that when a fast-spinning massive star that is at least 15 times the Sun's mass depletes all its nuclear energy, then its supercompressed core is crushed by the star's gravity and folds in on itself, giving birth to a black hole. Under the right conditions, the same phenomenon might occur to a smaller-scale star that undergoes a supernova explosion if much of its ejected mass collapses back onto the remnant crushed core. The uncountable tons of material around the star will start swirling and flowing into the black hole, and 2 jets of material will start blasting away from the black hole at near the speed of light. These jets can last for several seconds and create long-duration gamma-ray bursts, making up for a magnificent light show for anyone looking at them through a telescope thousands of light years away from it. The second scenario supports that in the center of a huge star, vast amounts of electrons and positrons, known as particles and antiparticles, find their lost halves and form dangerous gamma radiation. The opposite procedure happens as well, and this cycle goes on forever inside the star. Under special circumstances, this cycle might get out of balance just enough so that too many pairs of particles can form to the point that the star cannot keep its core under control, and it pops its guts out, forming a hypernova. The last scenario is very similar to the twin star solar systems for supernovae. If the circumstances are exactly perfect, and one of the stars explodes in such a spot and speed that releases its material exactly on its neutron star brother, then the latter becomes a very dense and unstable neutron ball, and an explosion might get triggered. It's a scaled-up supernova explosion that eventually might form a magnificent show, a hypernova. Scientists are still not sure which of the 3 mechanisms is more common, but if we know one thing, is all hypernovae are massively devastating and destructive. But how dangerous is a supernova? It wouldn't be a surprise if we told you that a typical supernova, and let alone a hypernova, are capable of constituting a planet like Earth uninhabitable if the event happened very close to our solar system. Imagine that there is a gigantic star 10 times larger than our Sun that would explode, forming a supernova only a mere 25 light-years away from our poor Earth. What would happen to us? Well, the explosion will trigger a blast of fast-moving, invisible neutrinos towards our planet. These are very small, slippery particles that carry vast amounts of energy that were originally trapped between the dying star's core and its atmosphere. They would arrive at high speeds, a tad slower than the speed of light, but thankfully, they're the least harmful of all the elementary particles that we know of. The real problems will start a few hours later, when an immeasurable number of photon particles would start arriving at Earth's atmosphere. An observer would be able to see the star's breathtaking explosion with a naked eye from our planet's surface. It would be like a small blinding spot in the sky, much smaller than our Sun, but definitely highly dangerous. In addition to the visible light, the exploded star would spit X-rays, gamma rays, and hard ultraviolet radiation into our atmosphere, completely destroying the Earth's ozone layer. All life as we know is fueled by sunlight, and by destroying the ozone layer, which is our planet's sunglasses, there would be unimaginable changes. The less ozone there is, the more UV light reaches the surface. Just a 10% increase in ground-level UV can be devastating to some organisms, such as phytoplankton. And since these organisms form the basis of oxygen production on Earth, and are the basis of all marine food chains, any significant disruption to them could trigger a mass extinction. But for such an event to happen, the supernova explosion must occur less than 50 light-years away from our planet. Additionally, any supernova closer than 1,000 light-years could still potentially have some kind of low impact on Earth's biosphere, but to a much lower degree. A hypernova, though, can be fatal even from distances of 10,000 light-years away, because of its jets that spew gamma rays at speeds close to the speed of light. However, the jet must be directly pointed our way in order to be fatal. The closest burst on our record, which is known as GRB 031203, was 1.3 billion light-years away, which, as you understand, was completely harmless. But since distances in space are extremely vast and most giant stars are millions if not billions of light-years away from us, there are not that many stars that we need to worry about that might die anytime soon. At present, there are no supernova candidates close to our solar system which are less than 50 light-years away, and only 6 near-Earth supernova candidates within 1,000 light-years. IK Pegasi, which is the closest candidate giant star at 150 light-years away from us, is estimated that by the time it could potentially go boom, our solar system will be at a safe distance due to the relative trajectories we're both traveling across space. Many experts seem to worry in the past about Betelgeuse from the Orion constellation, which is a very old star, 15 times the size of our Sun. However, it's been proved that even with the most pessimistic scenarios, there is a possibility of less than 0.1% that we're going to experience the supernova explosion of that star during our lifetimes, and most probably it won't do any kind of direct damage to Earth with ejected material. When it comes to radiation, such a supernova explosion might cause some effects on Earth's environment, but since it's too far away to harm our atmosphere, there'll only be a minor impact on life on our planet. As a little bonus, we want to share an interesting hypernova story. In 2016, a team of astronomers spotted an unusually bright object in the sky, only to discover that they somehow stumbled across the most powerful supernova on record. The ASASSN 15LH, which is located in a galaxy 3.8 billion light-years away from us, was actually so powerful it outshined an average supernova by almost 200 times and our Sun by 570 billion times. As a reference point, if you could somehow pull all 100 billion stars in our Milky Way galaxy into a blender, then pour the mix into the biggest sphere in existence, the ASASSN 15LH would still manage to shine 20 times brighter than it. Astronomers believe that they'll possibly never see a supernova this bright ever again. And let's hope that even if we're going to witness even a small-scale supernova, that it would be at such a distance that we could enjoy the fireworks and learn more about this magnificent phenomenon, but without the harm of any damage to our solar system. So, now you've seen how hypernovae are created and how deadly they are. Do you think we should be afraid of them? Let us know in the comments below. And if you enjoyed the video, give us a like, subscribe, and turn on the notifications to be the first to know when a new video arrives. Thanks for watching.